And Christopher, you want to start us off by reading the first two paragraphs here in number 1? Thank you. Keep going. One more.
For example, suppose we selected F14, Avery Bradley, Bogans, and Gerald Wallace from the 2013 Boston Celtics. Listed their heights at 6'9", 6'5", 6'9", respectively. We can write this corresponding names and heights using a set of ordered pairs.
Thank you very much. Okay, so one thing I want to highlight is Christopher used the word set, and then when he came down to the pairs, do you notice where the set, where the notation for set occurs? Yeah. Right here with those beautiful curly braces, right? So to read the set of ordered pairs, you would say the set of the ordered pair, Jeff Green, comma, 6'9". So what's important here is we're everything, pretty much everything we're talking about, a lot of the things we're talking about today will always have these curly braces around them because it's a set. We're going to be talking about sets. And we're going to be given some names to these different types of sets. So continue on for us, Andy.
This set of ordered pairs above is called a relation in mathematics. Relation is any set of ordered pairs.
Okay, so for some of you, that may be a new term for you, relation. And so you may want to highlight it. You may want to write it in your little vocabulary notebook, whatever. If you haven't heard of the idea of relation, it's simply the set of any set of ordered pairs. Okay, nothing really special about it. Any set of ordered pairs. Okay, so keep going, Andy.
Set of names: Jeff Green, Avery Bradley, Keith Hawkins, Gerald Wallace. It's the set of all first components of the ordered pairs is called the domain of the relation.
Okay, so let's stop there. Given that domain is highlighted or bold-faced, really important definition. So for our course, a set, notice that the domain is the set of the names. So when we represent the domain, we start off with these curly braces, and the set, the domain is the first component, so what we input into the ordered pair, what we typically call the X value, right? Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace all occur as the first component or the input in all of those ordered pairs we just looked at. This is called the domain of the relation. Okay, want to continue, Eliza? Okay, again, similarly with the domain, the range is a set. In this case, it's the set of heights, and that's usually typically occurs in the second position of your ordered pair, what we typically call the Y values, right? That's called the range of this particular relation. So we can visually see this. We can visually see this relation that we've listed up here, this set of ordered pairs, in a picture like this, where we could make the first sort of circle here. We can represent that with the name domain. Second circle looks a little different. It's not filled in. We could call that the range. And in the first circle, we can list each of the elements of the domain. Remember, the domain was a set, and each of the individual pieces of a set or elements here can be listed in the domain. And notice we only have 3 unique heights, 6'9", 6'2", and 6'5". And this little arrow says that Avery corresponds to the height 6 feet 2 inches. and Jeff corresponds to the height 6 feet 9 inches. Both Keith and Daryl, Keith corresponds to 6 feet 5. Daryl's also 6 feet 9. That's what that little arrow says. Okay. So in the ordered pairs above, we've listed the name of the Celtic player first and their height second. So let's mix it up. Let's just have fun with this relation. Let's decide to list the heights as the first component of what we would call the domain, and let's list the names second, or what we would call the range. So let's fill this picture in now for this relation, which is slightly different because we've reversed the order. So what would I write in this blue circle? You want to help me fill in this blue circle for the domain? Let's highlight this relation here so we know which one we're talking about. So the domain for the the domain for the green relation and the range for the green relation. Someone want to help me fill the domain in? Yep, Jesse? 6 feet 2 inches. Yep, I'll put a little dot. Yep. Yep. 6 feet 5 inches. Again, he only had to list the 3 different elements in the range. He didn't have to list 6, 9 twice. Okay. How about the range? Someone want to tell me what the range is? Okay. Yeah. I didn't put point. That's just to, you know, it's just like that's the point. I just put a dot there. I can take it away if it bothers you. Yeah, like a little bullet. Yeah. Okay. Okay, go ahead. Okay, perfect. Okay, and I know this is out of date, that some of these people that were on the roster the end of August 2013 didn't even make it to the season. And then where would I, if I were to draw an arrow from 6-2, where would I draw the arrow? Oh, okay, thank you. Boy, you guys are right on top of things. That's what I like. All right, Avery, right? Okay, and in fact, when I wrote this lecture, like the end of August, beginning of September of fall 13, and when we had it fall 13, my students, some of my students who are Celtics fans, already telling me they're not on the roster anymore. And I said, geez, I'm already out of date. It's only been a couple of weeks. Okay, so if I were to draw the corresponding or the second component for this first component, 6 feet 2 inches, who would it go to? 6 feet 2 inches. Avery, right? So I go draw an arrow down to Avery. 6 foot 9 inches. Can't hear you, Caitlin. Oh, so Jeff Green and Gerald, and 6'5" goes to Keith, right? Okay. All right. Yep. When you say in your own notes, do you mean my notes or your notes? Yep. Yep. That's fine. Yeah, it's all right. I got you. All right. So here we go. Here's our relation. Now you're the owner of the Celtics, and you've won the NBA championship, and you're walking into the locker room, and you want to hand out the most valuable player award to the player that's 6 feet 9 inches. Who would you give it to? Do you know from looking at this diagram? No. You don't. You can only give it to one person. You're confused. You're one of these absentee owners. You have no idea really which of those players was really the most valuable player. So you have a problem. And you have a problem because you look over here and you say, all right, here's 6 feet 9 inches, but I got 2 different players, 2 different arrows that go from 6 foot 9. One goes to Jeff Green and one goes to Gerald Wallace, and I don't know who to give it to. So we say, mathematics, this relation is not well defined. So in our course, we have to work with relations that are well defined, and those have a brand new name. So let's take a look at number 2. Anna?
So do you always make up the domain?
Excuse me?
Do you always go off the domain?
You start with the domain, and you see where it goes. And I think you'll have your answer in about 3 minutes, okay? All right. So I don't want to burst your bubble for you, okay? All right. So functions. All right. Jesse, want to read number 2? Okay, so here's your answer, Anna, right here. Okay? A well-defined relation, we're going to call it a function. And there's a couple different ways you can say it. One way is to say every output value has only one input value. There's only one output value for any input value. Excuse me, I said that wrong. Exactly one output value for any input value. Okay? Or each element in the domain, if that's where you want to start, Anna, there's one corresponding element in the range, and only one. Yep.
Is this the way it's for
Yes. She's a little ahead of you. Don't worry about that. We'll get there today. It's exactly the reason, Katie. All right. So in our basketball example, you know how we can assign usually a big capital letter to represent a set. We're going to say P represents this set and H represents this set. So at your seats, I want you to try this individually and then talk about your answers. I want you to identify which set of these ordered pairs represents a function and which set of these ordered pairs represents a relation. Isabel? I didn't say a relation was the same as a function. What I said is a well-defined relation is a function. So, but that's a really great question because let's talk about that for one quick second to distinguish. So here's a let's take the word rectangles, all rectangles in the world and all squares in the world, Isabel. There we go. What can you tell me about squares and rectangles in terms of making a relationship or an analogy with relations and, say, functions? In other words, yep, give it a try. Okay. Say that again. All right, so Katie says all squares are rectangles, but not vice versa, right? Does everybody agree with that? All squares are considered rectangles because what's the only way we define rectangles? Opposite sides are equal, right? Parallel sides are equal. Right? Are opposite sides on squares equal? In fact, it's even better. All the sides are equal. So you can be a rectangle and not be a square, but if you're a square, you're definitely a rectangle. And the same is true here with functions and relation, Isabel. Yeah. Okay? The relations are like the rectangles. Yeah, it's very like any kind of ordered pairs, set of ordered pairs, you'll match this. But to be a function, you only have one output for any input. Okay. All right, so go ahead. Answer A and B. Stop and put up your flag when you're done. Don't go on to 4 yet. All right. All right. So A, identify which set of ordered pairs. Let's do this by table. So table 1, 2, 3, 4, and 5, A and B. Table 1, what do you say for A? P, table 2. Table 3. B, table 4. Table 5. B. We don't have to discuss that. I agree. Okay. Table 1 for B. H. Table 2 for B. H. H and P. Table 3. Table 4. H and P. HP. In table 5. H and P. Okay. So we have a little bit of a disagreement here. 3 tables say that both the set H and P are considered relations, right? And 2 say just H. So this is like the rectangle and square idea. To be a relation, you're just a set of any ordered pairs. No special thing about you at all. All right? So both H and P represent a relation. Okay, H and P. Both H and P. All right? It's like anything goes when you're a relation, right? No special rules about you at all. All right, so let's take a look at this picture, and you try this on your own. I've given you 4 different pictures here representing domains and ranges. And yes, you can assume that the first oval you see represents the domain in each of these 2 visuals, okay? Domain and range. And any questions, put up your flags. When you're all done, let me know. Let's look at this. Okay, so let's take a look again at this first one. What does table 1 say about the first picture? Function, yes or no? Everybody's a yay? Okay, so, all right. And how would you represent the domain of this function? Someone want to give me their answer? Phoebe, Amy, Katie. Just like you said that, like that? Phoebe, Amy, Katie? Oh, yeah. Because what's a domain? It's a set. Yes. So you got to have your squigglies. And what else do you need in there? Between commas, right. Yes. Yes. Very good. How about the range? Sean?
The range,
Braces? Yeah. Okay. I agree with that. Okay, how about the second one? Is this a function? Yeah. It's a little tricky for people when they first see this because they see all of these domain values go into one value in the range and people get confused. And remember that for this to be a function, every single element in the domain can only go to one value in the range. And that's true. 0, you can follow 0's path. It just goes to 7, nowhere else. 3 goes to 7, nowhere else. -2 corresponds to 7, nowhere else. And 6 corresponds to 7. So that's definitely a function. Can you get that door for me? Thank you. It's a little noisy out there. So what's the domain look like here? Curly braces. And the range? Squigglies. Squigglies. All right, we'll call them squigglies. Yep. Yeah. In fact, I mentioned that in my first class. I said, oh, knowing my math lab, you're probably going to have to do this. Put it from the smallest to the largest. And someone said to me, I didn't have to do that because some people have worked ahead. Tom, you were working ahead, right, in the studio? Did you have to put them in order? No. So for the domain, they don't care. My math lab doesn't care. Okay, it's just when you do your interval notation, yeah? Okay? Your interval notation, which describes a set of numbers, your smaller number goes first, your larger number goes second, okay? So that's a good question. And I didn't know, and because I couldn't remember, I don't really do my math lab homework. I created which problems you had, in there, and I probably looked at them last year when we started my math lab, but I didn't remember anything about domains. So according to both Tom and this other students, the order doesn't matter. Okay, what about this last one here? Yes, no? Yay? Oh,
Oh, wait, sorry.
yes. And domain here is -1, 0, 1, 2, 3. And range is 2, 5, 3 curlies. Okay. That's a 2 with the, it's a 2 with the comma, right? I've been looking at too many student papers for too long. Nah, it's just my handwriting there. Okay. 2 comma. Okay. There's no 5 in the domain, which is the first, right? Okay, that's good. All right, how about this last one? Nay, boo. And it's because the input 3 does not correspond to, or map to 1 and only 1. 3 goes to 7, and 3 goes to -4. Okay, so it's definitely not a function. Okay. So that's sort of like two critical ideas about functions. Not only what is a function, its definition, but how do we look at the domain and range of a function? Okay, so today we're going to look at functions from a graphical perspective, an algebraic or symbolic perspective, a tabular perspective, okay? And so let's take a look at how we look at and visualize functions from a graph. So, Caitlin, you want to read us this, number 5?
If our corresponding sets are real fluid, this graph have a relation of all x of the relation.
Okay, so here we have now a visual. And here we have how many elements are in our, how many ordered pairs are in our relation from looking at this graph? How many ordered pairs? 5, right? We've got one ordered pair right here, second, third, fourth, fifth. Okay, so let's assign the coordinates for each point. You can do it at your seats, and I'll do it up here, and it should only take us a minute to do that, to label each of these points with the ordered pairs, the coordinates for each one. So I've done that. You can check what you've done with what I've put up here on the smart board. All right. So how would I define the domain for this particular relation? What would the domain look like? Squigglies? Okay, does everybody agree with that? Okay, so we have 1, 2, 3, 4, 5 points, but only 4 elements in the domain, because we have 2 points that go through x, have a coordinate at x equals 1 comma something else. All right, how about the range? Ryan, want to help me with that? Four and 5. Does everybody agree with that? And add 2? Oh, add 2 and 0. Okay, does everybody agree with that? Squigglies, absolutely. Full credit, you have to have your squigglies because the domain in a range is a set. All right. So does this represent a function, yes or no? No, I hear. Anybody say yes? Why do you say no? Caitlin, yeah?
There's the next coordinate.
Yeah, there's an x coordinate, which one? 1, that has 2 different y coordinates, one 4 and one -2. That violates a well-defined relation. That violates what being a function is. One can only go to -4 or 2. It can't go to both if it's going to be a function. So Katie, now it's your turn to see the vertical line test. Yay? So visually, Katie had asked a few minutes ago if this is why we use the vertical line test to determine whether something's a function. And if you imagine drawing a vertical line, in this case we have 1, 2, 3, we have 4 different inputs. So in this case, I only have to draw 4 vertical lines. If I draw a vertical line straight down through x equals -4, notice I only intersect that line with 1 point. That tells me for the value -4, I have 1 and only 1 output, 5. And if I draw a vertical line straight down through x equals -2, same situation. I have 1 output called 2. If I draw a vertical line down through 0, x equals 0, I have 1 output called 0. But when I draw a vertical line down through x equals 1, that's where I run into trouble. I have 2 outputs now, and that's my violation. So yes, there is a visual test to tell whether something's a function, and it's called the vertical line test. And we'll shortcut it by VLT. Now don't get hungry. It's not a BLT. It's a VLT. It's a veggie burger, lettuce and tomato. Okay. So a vertical line test determines if something is a function. Any questions on that? How the definition and this visual go together. It's kind of a neat thing. All right. So here's sort of a more formal definition of the vertical line test. One of the most important words here beside vertical is this. If any vertical line, not just a vertical line, any vertical line. So imagine having a vertical line that sweeps across your graph from left to right. And if any vertical line intersects that graph in more than 1 point, it's definitely not a function. Right? So in this first picture, as you sweep across, imagine this vertical line sweeping across. It only hits this graph, which is shown in red, in 1 point only. Whereas in this second picture, when we get to whatever this x coordinate is here, you could imagine it being 2 if you want, you hit the graph in 3 places. So this is not an example of a function. So next I've given you 3 more pictures. I'd like you to determine at your seats if these represent functions by using the vertical line test. Once you have agreement, put up your flags. Okay, so I think everybody in class agreed that this is a function, this is a function, and this is not a function. Is everybody okay with that? I mean, any questions, or you're still not sure? I mean, you might have said yes on some of this, but you're not sure, or you might have said no and you're not sure. Any questions at all before we move along? Okay, I asked you now that I didn't put this in the lecture notes, but given that we've just talked about domain and range, and I wanted you to see why we learned the notation we did on Wednesday, is that often to talk about a domain and range, which is a set of numbers, it's so much easier to use the interval notation. So does someone want to be brave and tell me what they wrote for the domain of this first function? Yeah, Isabel? Yeah. -3, right. So this graph starts at -3. That's the first x value, and it goes. So a really neat thing that we didn't do the other day on Wednesday, I didn't want to confuse you, so we were using solid dots and open dots on the number line, right, for the intervals. You can represent the domain just like this. Here's your real number line. Your x-axis is a real number line. We're including -3, and we're going all the way out to positive infinity. So you can sort of like use one thing to help you with another. You can sort of look at your x-axis here and then go from your visual down to your description using interval notation. Okay, so green's going to represent all of my possible x values, which start at -3 and go all the way out to infinity. Let's use blue to represent all positive y values, which is your range. Someone else want to tell me about range other than table 2? Anybody? Yeah, Caitlin? Bracket. 0. Okay. Agreement there? And you look at your graph and you say nothing from this graph is below the x-axis. So everything is non-negative, which means it's 0 or bigger. So on my graph, I put my staple like that at 0 and I color in all the way to infinity, and that represents my range. So my blue represents my range and my green represents my domain. No, I'm just showing you that when you're looking at a graph, that's what you look for to find your domain. You look along your x-axis. To find your range, you look along your y-axis. Okay? Now, B, we could spend 10 minutes talking about, and we're not quite ready. But to talk about the domain for B, you have to talk about it as 2 different sets with a union. You think we could do it? What do you think? Yeah, you want to try it? Let's see. We got 2 different sets, 2 different intervals. So who wants to give, this is a tough question. So if you didn't get it and you know, it's okay. We're not quite there yet. But what would be the domain of B? Anybody want to give it a shot? Well, let's see. Does this graph stop right there at -2? No, it goes like this. So that means all these points forever and ever is going to keep, okay? Yeah, so we want to start with what? Not braces, because we can't include infinity. Parentheses. Which infinity is it? I meant to say parentheses, negative infinity. So we're down here, we're way out here in the negative, and we're coming up, we come up, we reach some point there, and we start to come back down. Whoops, where am I? I'm on the wrong graph. We come up, and then we stop just before we get to what? 2. How close do we get to 2? Real close. Do we ever land on 2 with this graph? No. So how do I represent the end point here? Well, the end point is 2, but I don't include it. So that represents the domain from here all the way out here for that first little squiggly graph. Then, where's my next domain start? For the next part of my graph, this piece right here. Yeah, Katie? 2. And what do I put in front of the 2? Staple bracket, comma, and then what do I put here? Infinity. Okay. No, because the interval notation represents sets, so you don't have to, it's like redundant to put the curly braces in. That's where it gets a little tricky sometimes. You know, I'm really glad this class has down squiggly, 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 but remember the interval notation represents sets. The range is a little more challenging. We'll leave that. We'll just stop there. Okay. All right. So when we talked about this picture on the very second class, and you also talked about this picture for your project, okay? We looked at average cost of tuition and fees at public 4-year colleges in the United States. In our project, we used a linear model to describe this trend, but in our lecture notes on the very first day, we used this quadratic model. So it's real clear to us, I think, from looking and talking about this whole thing, that we have 2 different variables going on. One was the actual year, 2000, 2001, up to 2010. And the other variable here was the actual average cost to attend U.S. colleges for tuition and fees for each of those years. Okay, so we remember now when we use this model, we don't actually put in for X 2007, 2004. We just use the ending year. So we would go 0 for 2000, 1 for 2001, 2 for 2002, etc. We call the X variable in this model the independent variable, because it can be assigned any variable, any value in that domain, any value. All right? The domain in this situation isn't all real numbers because we have very discrete points. If we were to plot, when you plotted those 10 points or 11 points on your GeoGebra, you got 11 distinct points. So every number in the domain here look like 0 or 1 or 2 or 3 or 4 up to 10. We call those non-negative integers. Okay, so x is called the independent variable. The variable y is called the dependent variable because its value depends on x. Once you tell me an x, I can tell you what y is. I can tell you the average cost of tuition and fees. So you only can find the value of y after you select one of these independent variables, a value for the independent variable. Okay? So this model defines a function because for each value of x, for each of those school years, as I went from 2000 up to 2010, there was one and only one tuition, one and only one output. When I put a number into this model, I only get one y value. Okay, so this is definitely a function. And now we're going to change our notation. We're going to stop using y because we want to be more explicit and say that this value that I get for y really depends on what I put in for x. And the language we use for that is that it's a function of x. I keep forgetting. I'm so used to not having my pages go. Where my rest of this? Uh-oh. Where's number 10? Oh, there it is. I'm skipping this. You can read about this in your book. Read in your book. And this is what it's called, determining whether an equation represents a function. I don't know what page it's on, but it's in section 2.1. Okay. So let's talk about functional notation. So I first want to talk about functional notation with this table versus a graph or an equation. So take a look at this table, see what it represents. Take a few minutes to look at it. And I'm going to ask you a question to see if you can figure out which of these two variables, which is what we call the independent, don't anybody yell it out, which is the independent variable and which is the dependent variable. Just take a guess and write it beside, right here, beside time and height. Either write IV or DV, whatever one you think it is. Just take your own guess. You don't even have to compare and look at other folks at your table. So you make your own guess, all right? Nobody's going to know. Anybody want to take a shot at this? Which of these is the independent and which one's the dependent, Christopher? Okay, the height of the baseball depends on how many seconds have passed since this baseball has been hit. If you can say it, you can do it. So yes, the height is the dependent variable, and the time in seconds is the independent. Once you do that, you know something about the axes of your graph, because the independent variable always goes along your x-axis or your horizontal axis, and your dependent variable is your vertical axis. So you could label your graph right now if you wanted to. Yeah. And so you could start plotting each of these points. All right. So this idea of the height being clearly defined in terms of the time, we say it's a function of the time. And we use these letters, you know, not just those letters. Those are the common ones, little f, little g, little h, big F, big G, big H. These are often used to represent functions. And now, for functional notation, we replace y with this notation right here, f parentheses x. That is read as f of x. And this represents the value of your function at the value of x, whatever x is. So in this case, we might say the value of our function at 2 seconds, or 1 second, or half a second. X, whatever value of x is defined up here in our table, we can evaluate. The expression f of x does not mean f and x are multiplied. That's one thing that needs to be cleared up. There's no multiplication going on here, and I know it's a little confusing because when you first took algebra, you learned that parentheses could mean multiplication, but this is part of the functional notation. So instead of using x's and f of x's, f of x, or f of the input, is the same as the output value. F of the input is exactly the same as your output value. What goes inside these parentheses is your value of your independent variable. What comes out is the value of your dependent variable, inputs and outputs. Okay, so let's take a look at how we would evaluate this type of function. So here's the same table in number 12. And this now says, when I read this, I say, what's the output for f of 2? So in your mind, you say, I got to look for 2 as my input, my independent variable. And we just saw that time was the independent variable. So I go over to where it says 2. I identify x as 2. And then I see what is its partner. If I were to graph this, what would 2's partner be? 99. So 99 is the same as f of 2. So if I asked you to write the coordinates for this point, you most likely would say 2, 99. That's what we're used to doing. You wouldn't be wrong to say this, 2, f of 2. Because f of 2 and 99 represent exactly the same thing here. No, it's not wrong. No, if I'm saying this is intuitively how you would do it. One or the other, right? But here, and as long as I either have the table, Dylan, or a statement like this so I can see what f of 2 is, you'd be cool either way, okay? Then how might you write a sentence interpreting this particular input and output? You can see both the input here. Here's your input, 2 seconds. Here's your output. What I like to do when I'm asked to interpret is I come back to my ordered pair and I always put in right after the number the actual unit. So then it really helps me to write my sentence, and I remember to put everything in my sentence that I'm supposed to. Anybody want to give me a sentence to interpret this, Jesse? Baseball's at 99 feet. Fine. Anybody else want to give me another interpretation or another sentence? Does that do it for most of you? Yes, no? Okay. How about someone want to tell me what f of 0 is equal to? F of 0. Anybody? 3. All right. We go to our table, we find 0 because this is our inputs, time is our input, or our independent variable, height is our output, or our dependent variable. Again, all interchangeable vocabulary and words. Now, this is an interesting sentence to try to write. I'd like you to try to write the sentence that interprets this output and this input. So you just give it a shot, take 30 seconds, write down a quick sentence. It means it has a subject and a verb, thank you. Starts with a capital letter, ends with a period, thank you. Someone, who haven't I heard from today? Evan, I haven't heard from you. You want to give this a shot? You can always pass if I ask you. You never have to answer, you always can pass. Evan?
Yo, that's 0 seconds. It's small. I guess you could say this starts with 0 seconds.
At 0 seconds, the baseball is at 3 feet. Fine. Anybody else? Some other way of saying that, Katie? At 0 seconds, when the ball hits the bat, the what? The height. Good. You getting that? The height is 3 feet. Okay. Another way. Yep. Eliza? The ball has an initial height, and I'm going to underline that word initial, height of 3 feet. And I'm actually going to edit your sentence, and I'm going to stop right there. because I don't have to say at time 0 seconds, because there's a word there, initial, that means t equals 0. Initial means time equals 0, or whatever your horizontal variable is set to 0. So when you use the word initial, it really kind of takes away the sort of like awkwardness of saying at 0 seconds sometimes. You say initially, and you've got that t equals 0 seconds covered, right? I'm not saying any of these are incorrect or that you have to use the word initial. I'm just saying that that's typically a standard way of representing this. Yep. All right, so basically I'm just asking about what that 03 means, okay? And remember, back to your project, I hope you read my comments. Whenever you have a pair of coordinates, an ordered pair, what's critical? All relevant numbers can be seen somewhere in the sentence, and all relevant units. So we don't have to talk about everything in between, Anna. You can just say, hey, at 0 seconds, or when we initially went to smack this ball, the height of the baseball was 3 feet. Okay? All right. All right. Keep it simple, silly. I would never say that other word. All right. You've heard of KISS, right? Yeah? All right. F of x equals 23 is a little different. What's this? How would we? This is asking you to solve an equation. They're saying, what value of x gives me an output of 103? And what would x be here? 2.5. X is 2.5. When we write about it, we add on our seconds. X is just a number. So what would I say here to interpret this one? Let's just, someone, Hannah, how about you, Hannah? At 2.5 seconds, the ball reaches a height of 103 feet. Can you tell me anything else about that 103 feet? It's the peak. It's the maximum value. So the ball reaches a maximum. We're not covering it yet, but that's a really important critical point. That's actually a calculus term. Okay, maximum height of 103 feet. Maximum height. Okay. So I know, Tom, you have to leave early on Fridays, so go ahead. You know everything you need to know for Monday? Okay. All right, so that's representing the function using a table. The same information can be expressed here with an actual algebraic or symbolic equation. So let's use this equation to find f of 2. Well, you'd say, we just found f of 2 back here at 99. So let's do it here. How would I do it here, f of 2? What would I do? Anybody want to help me?
You insert the 2 as the input of that.
Yeah, so what do I do?
So you would insert 2 as input, fill it in as equation 16, negative 16, parentheses, 2x
Yeah,
plus 80.
yeah, yeah. Okay, and what does this equal? F of 2, right? And so we're going to evaluate it because we've got this equation. So I'm going to, this is negative 64 plus 160 plus 3, and that comes out to be 99. Does that agree with our table? Okay. Use the equation to solve f of x equals 99. Now I'm not asking for the output given an input. I don't know my value of x. I'm trying to find it, so I've got to solve this equation. So what do I do with this 99? Where do I put that? Yeah, where y goes, or in this case, where f of x is, which is taking the place of y. So now we do this. 99 equals negative 16x squared plus 80x plus 3. What kind of equation? quadratic, so a little review for Monday's test. Oh, all right. How are we going to solve this? Yeah, we're going to set this equal to 0, so we subtract 99 from both sides. And we get 0 equals negative 16x squared plus 80x minus 96. Do you want to factor this right-hand side of the equation? Are you like really like jumping for joy to factor that? No, why not? It's scary. Can you make it less scary? Factor, greatest common factor is your greatest common friend. Absolutely. Without this beautiful friend, you are going to sit here forever, or guess what? You might use your quadratic formula and your numbers are big and you're like, oh, right? So here's our equation. I have the right to multiply or divide both sides of any equation by any non-zero quantity. Why not pick 16? And I'm going to ask you, is there a better number than 16? Negative 16, because what do I want in front of x squared so I can factor it really easily? 1. So I'm going to divide both sides by negative 16. Well, when I divide 0 by negative 16, I get 0. Negative 16 divided by negative 16 gives me 1x squared. Cool. 80x divided by negative 16 gives me minus 5x. And negative 96 divided by negative 16 gives me a beautiful positive 6. Would you like to factor that now? Oh, yeah, cool. X minus 2, x minus 3. So when x is 2, my ball's at 95 feet. And when x is 3, my ball's at 95 feet, my baseball. So the moral of the story, when you come in here on Monday, if you have to do any factoring on the test, which you will, what? Nope, because it's negative 96 divided by negative 16. Okay, that's all right. You don't have to apologize. I make mistakes all the time. All right, so you can see that answer right here on your graph, folks, right? We asked, when is this ball at 99 feet? And all I would do is come up here to 99 feet, and I would draw a horizontal line straight across at y equals 99, and you see I go through 2 points. If I wanted to find when the ball's at 67 feet, I draw a horizontal line straight through, and I see when x is 1 and 4. To find f of 4, I say, oops, where's my 4? That's my input. So I go to my x-axis to 4, and now I draw, hey, I don't want you. Get out of there. I draw a vertical line. Here's 4. What does 67 represent? F of 4. My height at 4 seconds is 67 feet. So if I give you a table, you should be able to evaluate various values of your function for a given input, or find the inputs for various outputs. If I give you a graph, same thing. If I give you the function as an equation, same thing. You're going to be asked to evaluate values for a function several different ways. Okay? You now have not a whole lot of time, 6 minutes, so I'm going to stop you. And I'm going to say that when you come in here on Monday, you have a test. This information is not on that test. But you have an entire week between now and next Friday to do this. Do not come in here next Friday without this done, because we're going to keep talking about functions. And it's really critical that you work through and understand this activity, how to interpret functions and the notation. Okay? Now, let me also point out that the answers are given to you for everything. And it's really tempting to sometimes when you're stuck to like take a quick look at the answer. So try each of these on your own first. Just try them and try to avoid the temptation of looking at the answers. Do I have a promise you're going to do this by next Friday? Okay. And so what happens on Monday with your test? You can take in 1 page of notes, both sides. You could take this pink sheet in and have anything written on the back. What time can you start? What time can you start? 10 o'clock. I will be in the studio, but I will come in and give you your test and get you going. Okay? I'll see you on Monday. Have a good weekend. Study hard.